Namaste. Welcome to today's lecture. Today I'm going to speak on the topic of scanning electron microscopy. What are the principles based on which this instrumental technique is developed and how it can be applied for the standardization of Ayurvedic formulations. At the outset, let me thank Ayurveda Network 𝐕𝐢, especially Dr. Kishore, for giving me this opportunity to be a part of this educational program. We all accept that safety and efficacy of Ayurvedic formulations to a great extent depend on the quality of the product. When quality of an Ayurvedic formulation is assured, hopefully to a great extent, safety and efficacy are also taken care of. Quality control, quality assurance, and standardization of Ayurvedic products have remained a great challenge since a pretty long time. That too in the case of 𝐻𝐸dhi or herbo-mineral formulations. This is because the raw materials that we use in the preparation of 𝐻𝐸dhi themselves are not properly standardized. They are not properly characterized. They show great variations also. At the same time, we are also following a number of complex procedures while preparing 𝐻𝐸dhi. Due to these reasons, it's very difficult for us to predict the structure of the final product. Elucidation of the complex structure and its correlation with the pharmacological activity becomes a very tough job. That is the main reason that still we are facing challenges in the standardization of Ayurvedic herbo-mineral formulations. Of course, for the past 2 decades, we have worked a lot in this direction. Ayurvedic pharmaceutical companies, academic institutes at the level of post-graduation and PhD studies, or at the level of M.Pharma studies, and also various other research organizations, parallel scientific disciplines, they are all working in this direction. When we observe the development that has taken place in the parallel sciences, that helped us a lot to incorporate certain modern advanced techniques in the field of Ayurveda for the standardization of Ayurvedic formulations. In the field of physics, chemistry, that too inorganic chemistry, biochemistry, biotechnology, pharmacogenomics, pharmacology, and applied scientific fields like instrumental engineering, etc., has helped us to understand that there are many techniques that are emerging which can be utilized for better understanding of complex structure of our 𝐻𝐸dhis, and those tools can be judicially planned and incorporated for this standardization. One such technique is scanning electron microscopy. All of us agree that particle size is a very important factor that decides therapeutic efficacy of Ayurvedic formulations. Finer the particles, better will be the absorption and bioavailability. This is more important in the context of bhasma and pishti-like preparations. In bhasma pariksha, as we know very well, tests like rekha purnata, varitaratva, unama all help to ensure the fineness of the particles. We have been telling that bhasma, certain sindura, certain pishti preparations show the presence of nanoparticles in them. presence of nanoparticles and microparticles could be revealed by using techniques like scanning electron microscopy. There are many modern analytical techniques that are adopted to understand particle size and particle distribution. To quote a few examples, dynamic light scattering technique, laser diffraction technique, transmission electron microscopy, atomic force microscopy, and today's topic, scanning electron microscopy. So it is essential for us to understand at least basics of this technique so that its applied aspect can be better understood. I am sure that most of you must have read several articles where use of scanning electron microscopy for the standardization of Ayurvedic formulations are described. Some of you might have used this technique to analyze your research products also. Anyway, let us try to understand some important principles, instrumentation, and application of scanning electron microscopy. Considering the length of the topic, I have planned to divide my presentation into two parts. Today I will be focusing on scanning electron microscope, and in the next class I will be talking on its specific and general applications. As I said, the topic is entitled as Application of Scanning Electron Microscopy in the Analysis of Ayurvedic Herbo-Mineral Formulations. Today I will be focusing on scanning electron microscopy specific. Contents of my presentation include an introduction, history, scanning process and image formation, magnification, instrumentation, sample preparation, comparison of optical microscope, transmission electron microscope, and scanning electron microscope, characteristic information obtained by scanning electron microscope, general applications, and finally Ayurvedic applications. So let me try to discuss up to instrumentation in today's class, and in the next presentation I will speak about sample preparation, comparison of OM-TEM and SEM, characteristic information obtained by SEM, general and specific Ayurvedic applications. So let us start with the introduction. The scanning electron microscope is a type of electron microscope that images the sample surface by scanning it with a high energy beam of electrons in a raster scan pattern. Let us try to understand this definition. The scanning electron microscope is nothing but an electron microscope. Here, sample surface is imaged. How the image is generated? By scanning sample surface with a high energy beam of electrons. What is the scanning pattern? Scanning pattern is a raster scan pattern. What is this raster scan pattern? A raster scan or raster scanning is the rectangular pattern of image capture and reconstruction of it in a monitor. In raster scanning, the beam here, beam of electrons, sweeps horizontally left to right at a steady rate, then blanks and rapidly moves back to the front, moving towards the left, where it turns back on and sweeps out the next line. During this time, the vertical position is also steadily increasing, that is downwards, but much more slowly. There is one vertical sweep per image frame, but one horizontal sweep per line of resolution. I will make it very simple. It is nothing but scanning in a rectangular fashion. It is not like a direct focusing at a single point as we see in the case of an optical microscope. Here beam of electrons will move horizontally and vertically in a rectangular fashion, line by line. That is called as a raster scan, and this scanned image is recreated. Let us understand this in coming slides. The electrons interact with the atoms that make up this sample, producing signals that contain information about the sample's surface topography, that is how the surface of the sample looks, composition of the sample, and other properties such as electrical conductivity. It may not be so important in the case of Ayurvedic formulations, of course. Scanning electron microscope not only shows you the particles and its size and distribution at the area of focus, it also gives you an idea about how the surface looks. It gives you the three-dimensional image of crystals if at all present. When it is coupled with IDAX or EDS, it also gives you an idea about the elemental composition at the area of focus. Regarding electron microscope, an electron microscope is a type of microscope that uses a particle beam of electrons to illuminate a specimen and create a highly magnified image. Here, as I already mentioned, we are using particle beam of electrons which illuminate the specimen and that creates a highly magnified image. Electron microscopes have much greater resolving power than light microscopes. Light microscopes use electromagnetic radiation, that is a visible light, and they can obtain maximum, that is the best variety of light microscope can obtain a maximum magnification of about 2000x. In comparison to that, electron microscopes can have much greater resolving power. It may be even 1000 times more than that of best light microscope. That is maybe up to 2 million times or 20 lakh x. When this electron beam interacts with the sample, the types of signals produced by an SEM include secondary electrons, back scattered electrons, characteristic X-rays, light, that is called as cathodoluminescence, specimen current, and transmitted electrons. Let me repeat. The types of signals that are produced by an SEM include secondary electrons, BSC or backscattered electrons, characteristic X-rays, light, there may be even Auger electrons also, specimen current, and transmitted electrons. So by these names, at least you can understand that some are backscattered, some are passing through the sample, and some are transmitted through the sample and come out from the other side. These are different types of signals. We will understand them better. Out of all these signals, secondary electrons are most important. major portion of the signals generated when electron beam falls on the specimen are secondary electrons. So in all scanning electron microscopes, secondary electron detectors are common. And also it is very rare that a single machine would have detectors for all possible signals. It is very, very difficult to get an instrument which has got detector for secondary electron, detector for auger electron, detector for backscattered electron, detector for X-rays, all these. Of course, if there are multiple detectors, you will have better information, better resolution. But if you are having a detector only for secondary electrons, that itself is sufficient for most of the purposes. The signals here result from interactions of the electron beam with atoms at or near the surface of the sample. This picture will give you an idea about various signals that are generated. So when an electron beam strikes a sample, a large number of signals are generated. So this is the platform or a stage in which sample is mounted. We call this as a teardrop sample. We can see the shape is like a drop of tear. Here electron beam, a beam containing electrons which are thrown out from an electron gun, falls on this specimen. Then we have backscattered electrons. Some amount passes through the sample, that is called a specimen current, and some pass beyond the sample, they are called as transmitted electrons. These transmitted electrons may be elastically scattered electrons or inelastically scattered electrons. What are these? In the simplest words, elastic scattering is a form of particle scattering in scattering theory, which is especially described in nuclear physics and particle physics. In this process, the kinetic energy of a particle is conserved in the center of mass frame, but its direction of propagation is modified by interaction with other particles or potentials. In simplest terms, so when you have a particle beam like this falling on the specimen and it passes through it, whatever kinetic energy that is present in the incident beam, same is preserved in the scattered beam also, but its direction of propagation is changed. That is elastic scattering. What about inelastic scattering? In chemistry, nuclear physics and also particle physics, inelastic scattering is a fundamental scattering process in which the kinetic energy of an incident particle is not conserved. In inelastic scattering process, some amount of the energy of the incident beam will be either lost or sometimes it may be increased also. That means it is not the same kinetic energy that is conserved. In the signals that are coming backwards, most important signals are in the form of secondary electrons. We have a small amount of X-rays also and a small amount of something known as auger electrons. You may be knowing about the auger effect. The auger effect is a physical phenomenon in which the filling of an inertial vacancy of an atom is accompanied by the emission of an electron from the same atom. That is, when an incident beam of energy falls on an atom, from the inertial, an electron may be knocked out. This space is filled by an electron from higher energy level. An electron from higher energy level falls into the vacancy. During this process, energy is released. This is called as an auger effect. It may be in the form of auger electrons. We also have cathodoluminescence here. Cathodoluminescence is an optical and electromagnetic phenomenon. Here, electrons impacting on a luminescent material such as phosphor, for example, cause the emission of photons which may have wavelengths in the visible spectrum. If you are taking the entire electromagnetic spectrum, cathodoluminescence is light, or it is the electromagnetic radiation ranging from the ultraviolet to the NIR or near infrared region in the electromagnetic spectrum. That is nothing but the visible region. So these are the various types of signals that are generated in electron microscope. As I already mentioned, in the most common or standard detection mode, secondary electron imaging or SEI, the SEM can produce a very high resolution image of a sample surface. A scanning electron microscope, a standard basic type which has only secondary electron detector, can give you a resolution to that extent that you can reveal or see the presence of particles which are in the range of 1 to 5 nanometers. The electron beam that falls on the specimen is very narrow. Because of this, SEM micrographs have a large depth of field. When electron beam is narrower, better will be the penetration into the sample depth. Because of this, a characteristic three-dimensional appearance will be seen in SEM micrographs. This is very useful for us to understand the surface structure of a sample. You can see in this picture, this is a scanning electron microscopic image of pollen grains. See how beautifully three-dimensional image is created here so that you can easily understand the structure of the pollen grains. Now let us talk about history of scanning electron microscope. In short, how SEM was developed. The first scanning electron microscopic image was obtained by a scientist known as Max Knoll. It was in 1935 when he obtained an image of silicon steel showing electron channeling contrast. Further, this work was pioneered. Physical principles of scanning electron microscope was understood and explained, and beam specimen interactions were performed by a scientist known as Manfred von Arding in 1937. He produced a British patent for this, but unfortunately, he never made a practical instrument. Practical scanning electron microscope was developed quite late. It was in 1965 when the first commercial scanning electron microscope was developed and marketed by the Cambridge Instrument Company. They named it as StereoScan. It was Professor Sir Charles Oatley and his postgraduate student Gary Stewart developed this particular instrument. That's about the history in short. Now let us talk about the scanning process and image formation. How the scanning process is being done here and how the image is formed in scanning electron microscope. In a typical SEM, an electron beam is thermionically emitted from an electron gun fitted with a tungsten filament cathode. We understand this very clearly. Electron beam is thermionically emitted. That means when a material, say a metal, is heated at a particular temperature, it will emit electrons. This is possible only in such metals which have a high melting point, because you have to heat the metal to a great extent so that it emits electrons. So these electrons are known as thermionically emitted electrons. Practically, these are emitted from an electron gun that is fitted with a tungsten filament cathode. Why tungsten is used here? Tungsten is normally used in thermionic electron guns because it has the highest melting point. It has the highest melting point of all the elements discovered. Its melting point is about 3422 degrees centigrade. At the same time, it also has lowest vapor pressure of all elements. To be more specific, of all metals, thereby allowing it to be heated for electron emission. At the same time, it's also cheaper because tungsten is a very common filament that is used in electric bulb. This is how an electron gun looks, which contains tungsten filament in it. Further, the electron beam which is generated here typically has an energy ranging from a few hundred electron volts to about 40,000, that is 40 kilo electron volts, and it is focused by one or two condenser lenses to a spot about 0.4 to 5 nanometer in diameter. We have condenser lenses in the instrument of electron microscope, which helps to focus this electron energy beam at a very, very narrow spot ranging from 0.4 to 5 nanometer. We will understand this later in instrumentation. The beam produced here passes through pairs of scanning coils or pairs of deflector plates in the electron column. Electron microscope has a column where a pair of scanning coils or deflector plates are fixed. Typically in the final lens they are present. They deflect the beam in the X and Y axis so that it scans in a raster scan fashion. As I already mentioned, these scanning coils will deflect the beam of electrons in X-axis along Y-axis so that in a rectangular fashion raster scanning occurs. When the primary electron beam interacts with the sample, the electrons lose energy by repeated random scattering and absorption within a teardrop shaped volume of the specimen, which I had already shown you in the schematic diagram. And this teardrop shaped volume of the specimen with which electron beam interacts is called as interaction volume, and this volume may extend from 100 nanometer to maximum 5 microns into the surface. This size of interaction volume depends on various factors, like say electrons landing energy, the atomic number of the specimen, the specimen's density, etc. The energy exchange that is happening between the electron beam and the sample results in the reflection of high energy electrons by, as I already mentioned, elastic scattering, emission of secondary electrons by inelastic scattering, and emission of electromagnetic radiation, that is cathodoluminescence, each of which can be detected by specialized detectors. The beam current is also seen here, which is absorbed by the specimen, is also can be detected, and it also will help you to create images of the distribution of specimen current. Electronic amplifiers of various types are used in this instrument, and these amplifiers amplify the signals which are displayed as variations in brightness on a CRT, that is cathode ray tube. The raster scanning of the CRT display is synchronized with that of the beam on the specimen in the microscope, and the resulting image is therefore a distribution map of the intensity of the signal being emitted from the scanned area of the sample or specimen. Understand very carefully. In the display device also we have rasters, and they are synchronized with the raster scanning that is happening by the beam on the specimen, and this results in the distribution map of intensity of the signal which is being emitted from the scanned area of the specimen. How magnification occurs here? It's not like an optical microscope where a lens decides the magnification. So provided the electron gun can generate a beam with sufficiently small diameter, an SEM could in principle work entirely without condenser or objective lenses. But it may not be so versatile. By principle, as I already mentioned, electron gun generates a very, very narrow beam of electrons. When you have a very narrow beam of electron which can act upon a very, very small diameter, definitely scanning electron microscope will be giving you good magnification. But when you have condenser or objective lenses, this diameter of interaction will be still narrower, so that magnification will be even better. Very high resolution can be resulted. In SEM, as in scanning probe microscopy, if at all you have studied SPM, you will understand, magnification results from the ratio of the dimensions of the raster on the specimen and the raster on the display device. When you have a very, very smaller area that is scanned and large raster in the display device, you will have better magnification. The image may be captured by a photography. In newer instruments, it is not a photography. In cathode ray tube, the image is created and it is digitally captured, and it is displayed on a computer monitor, and it can be saved to a computer's hard disk. So magnification in an SEM can be controlled over a range of up to 6 orders of magnitude. In a very basic type of instrument, from 10 to 5 lakh times magnification can be observed. In a high proficiency instrument, it can be up to 2 million x. Unlike optical and transmission electron microscopes, here image magnification is not a function of the power of objective lens. SEMs may have condenser and objective lenses. They do have, but their function is different. Their function is to focus the beam on a spot, not the magnification. Suppose we assume that the display screen has a fixed size. It is true also. Display screen has a fixed size. It is not going to change. Higher magnification can be attained when you reduce the size of the raster of the specimen, and vice versa. That is, if larger raster is scanned in the specimen, smaller will be the magnification. If smaller will be the area that is scanned, larger will be the image. Magnification is therefore controlled by the current supplied to the 𝐿 scanning coils or the voltage supplied to the 𝐿 deflector plates, and it is not by objective lens power. Now let us talk about the instrumentation. This is the actual instrument, how it looks, courtesy IIT Kharagpur. Number one here is a column which generates a beam of electrons. Number two here is a specimen chamber where the electron beam interacts with the sample. Number three are the detectors. It may be secondary electron detectors or other detectors also to monitor the different signals that result from the electron beam and sample interaction. The fourth here is a monitor, or it's a viewing system that builds an image from the detector signal. So let me give you a better picture here, a schematic diagram and the actual column. At the top you can see here an electron gun which generates electron beams thermionically. Here we have gun alignment control, which controls the alignment of the electron gun so that energy beam that is thrown out passes in a specific direction. Once it is done, we have a pneumatic airlock valve here which fixes the position of electron gun. Next we have condenser lens here which will focus the beam or still narrows the electron beam. Here we have objective aperture. Here we have scanning coils and objective lens. They have deflector plates which help to move the beam of electrons in a raster scan fashion on the specimen. The specimen here is mounted on the stage. This is a motorized stage and this is the sample chamber. Here, this is the close-up image of detectors that are used. This is a very good instrument where we have multiple detectors. We have secondary electron detectors. We also have EDS detector here. We also have backscatter detector here. So this is a close-up image of sample stage, and this is the strub where the sample is mounted. So this is how the image is created on the monitor. So this is how we have to see through the lens in optical microscope. In scanning electron microscope, magnified images are created using electrons instead of light waves. I will show you the instrumentation schematically step by step. In this picture you can see a column here and at the top an electron gun. Here we have condensing lenses. This column is vacuum now, and here at the lower end you have objective lens. So after the air is pumped out of the column, because vacuum state is very, very important in electron microscope. So after the air is pumped out, an electron gun which is present at the top here emits a beam of high energy electrons. This beam travels downwards through a series of magnetic lenses designed to focus the electrons to a very fine spot. In this second image, you can see the scanning coils here at the base. Near the bottom, a set of scanning coils that moves the focused beam back and forth, left and right in a raster scan fashion on the target. As the electron beam hits each spot of the sample, here, secondary electrons are knocked loose from the surface. A detector counts these electrons and sends the signals to the amplifier. This is a final image where you can see that the image is built up from a number of electrons emitted from each spot on the sample. It is displayed on the monitor. Let me club all these images and show you. So this is how the scanning electron microscope is revealing you new levels of detail and complexity in the amazing world of microorganisms and miniature structures. This is the combined image. We have electron gun at the top. This is the vacuum column. These are the condensing lenses which further narrows down the electron beam and focus it to a small area. These are the scanning coils. These are the objective lens which deflects this electron beam in a raster scan fashion over the target. Secondary electrons are generated. They are counted by the detector, amplified, and the image is created on the monitor. So let me give you an animation so that you can better understand this.
Work. Inside the microscope station is an electron gun, similar to the one you monitor or watching. There are also several coils, condensing lenses, a scan coil, and the objective lens. Finally, there is the target. The condensing lenses focus the electrons into a tight region. The scan coil makes the beam play over the target, and the objective lens helps to focus the image. As the beam plays over the target, secondary electrons are not released. These are gathered by the detector, amplified, then fed to the display, where the final image is created.
I hope it is clear now. This is the scanning electron microscope of blood cells. You can see biconcave structure of red blood cells here. A beautiful three-dimensional image. This is how an ACM chamber looks like. We will stop here today. We will continue with other aspects like sample preparation, general and specific applications of scanning electron microscope. Thanks for joining me. See you in the next class soon. Till then, continue enjoying learning process. Goodbye.